All right, welcome everybody. Today we are going to talk about Calc Lesson number 23. We're going to call this section 2.6, Related Rates Day 1, and we're going to focus today on circles and spheres. You already had an introduction day to related rates. So if you kind of think back to the kinds of things that we did during that lesson, we talked about how you take the derivative with respect to t. Of course, that's d dt. Basically, you take all your derivatives like normal, but follow it up with a d whatever dt, depending on the variable. You saw a few examples where you had to plug in some values and then solve for something. And then you saw some problems where you had to read the problem, you had to set up some kind of an equation, and then you had to differentiate with respect to t. So now we're going to kind of put all those things together. You already saw a list of some of the most common types of shapes and scenarios that you're going to see throughout this unit. But again, today we're going to focus specifically on circles and spheres. So first off, let's go ahead and take a look at the important formulas that you're going to be using in this unit. You have a list of them not only in your notes packet, but also in your homework packet. For the majority of the problems, drawing a picture is usually going to be a vital step in your solution process. Not as much so today with circles and spheres. Obviously, you can see one of each below. Because those shapes tend to be a little bit more universal, whether you draw them for circles and spheres is kind of up to you. But I think you'll see in upcoming lessons why drawing the shapes will become helpful. So taking a look at this list of formulas, as we go through the unit, you of course would want to note what each formula stands for. In the past, you would have had to memorize them, but now, since it's open notes, that shouldn't be an issue. So the first formula, A equals pi r squared, that is of course the area of a circle. Then V equals 4/3 pi r cubed, that is of course the volume of a sphere. And again, just in case we didn't know, that's area of a circle. That's volume of a sphere. And then if you take a look to the right, A equals 4 pi r squared. That is the surface area of a sphere. So those are all important formulas that we're going to use today. Take a quick minute to look at those two formulas for the sphere. Look at the volume formula, then look at the surface area formula. Do you see a relationship between the two? Hopefully, if you look carefully, you see that to find the surface area formula, you simply take the derivative of the volume, which if you kind of think about everything we've done this year, that should actually make perfect sense. So again, you can make a note here on the first sheet as to those three formulas. Otherwise, we're going to kind of list them and use them throughout. So here in number 1, a golf ball is chipped into a water hazard that creates a circular ripple effect. If the radius of the ripple is increasing at 0.8 meters per second, how fast is the area changing when the radius is exactly 6 meters? So first of all, I know that the font is a little bit small, but hopefully you should all have your very own copy, so it should be relatively easy for you to follow along. Again, drawing a picture is normally going to be one of our steps, but because it's simply going to be a circle, whether you draw it or not is really kind of up to you. So the fact that we are talking about a circular ripple effect and the fact that we are talking about how fast is the area changing, that's how we know that the relevant formula is going to be the area of a circle, which of course is pi r squared. Then if you take a look at the setup that you have here, if you were to flip through your note packet, you'll see that this box setup is present for the first couple of days. We have found in years past, this is kind of a really nice way for you to set up all the information and then ultimately solve. And then as you get to the later half of the packet, you can see those boxes kind of disappear. And then you can play a little more fast and loose with the process as you get better at it. So starting here with the known quantity. So the known quantities are anything that is explicitly stated in the problem, and you of course want to assign it appropriately to the variables. In this problem, we have the variable of a, which means that there'll eventually be a derivative, which means we'll have dA dt. There's also a variable r, which means we'll eventually have a dr dt, and pi is of course a constant, so you would treat it as such. So in terms of the known quantity, the radius of the ripple is increasing at 0.8 meters per second. So if you know how fast the radius is changing, you know dr dt, and that would be 0.8 meters per second. Then you want to find how fast is the area changing when the radius is exactly 6 meters. So we know that the radius is exactly 6 meters. We're trying to find how fast is the area changing, which means we're ultimately looking for dA dt. And if you take a look at what we have here, this is basically all of the information. Kind of try to envision what's happening here. So imagine, if you've ever seen a lake or a pond, when something is dropped into the water and the ripples that it makes. Obviously, the radius of those ripples is not the same at every instant, which of course means the area would not be the same. So that's the whole point of related rates. It's not the same the whole time. So you're trying to solve at one particular instant, which in this case is when the radius is 6 meters. I want you to note, though, that sometimes you have to be a little bit of a detective. Instead of them saying, solve this problem exactly when the radius is 6 meters, they could have said after 7.5 seconds. If they had said after 7.5 seconds, you would, of course, take 7.5. You would multiply it by 0.8 meters per second, and that's how you would get a radius of 6 meters. So again, you always have to have the information that you need in the problem. Sometimes you just have to do an extra calculation step before you can actually go ahead and plug it in and solve. So right now, this is all the information that I have. So I'm hoping that when I go to solve, I have everything that I need. So when we go to differentiate with respect to t, we're of course going to differentiate a equals pi r squared. So the derivative of a is 1 dA dt. Put the 1 or don't, it's up to you. Pi is a constant, so you're going to bring down the 2 times pi. You're going to do r to the 1 less power, and then you're going to follow it up with dr dt. And to be honest, that's kind of as far as we had gone on the introduction day. You had a formula and you had taken the derivative, but now we're going to go ahead and solve it all the way through. So we are, of course, trying to solve for dA dt, so that remains the variable. 2 times pi, the radius, 6 meters. dr dt is the rate at which the radius is changing, which is 0.8 meters per second. And if you go ahead and multiply everything on the right-hand side through, including the units, so 6 times 2 pi, that's 12 pi. 12 pi times 0.8 is 9.6 pi. And then if you multiply meters times meters per second, you're going to get a unit of meters squared per second. And that is your very first related rate problem all the way through. So are they always going to be this easy? No. Are they always going to be this easy today? Kind of. But each day is going to kind of focus on a different group of shapes and scenarios. And again, today is all about circles and spheres. So a couple things to point out here. It would probably it'd be your best interest most of the time to just leave the final answer in terms of pi. You can make it a decimal if you want to. If you are going to round it, you're always going to round it to the nearest hundredth only. My advice, though, would be just to leave it in terms of pi where possible, which happens most of the time. But again, if you are going to round, you're only going to round to the nearest hundredth. That's it. Then a note about the units here. So you have to have the correct unit in your answer, meters squared per second. If you are able to kind of skip writing the units all the time and then have it correct in your final answer, that's fine. But at least at first, you might want to think about putting it in for every step just while you're getting used to the process. So let's go ahead and try another one. Air is being pumped into a spherical balloon. So a spherical balloon is, of course, a sphere, so that its volume is changing or increasing at a rate of 80 cubic centimeters per second. How fast is the radius changing when the diameter is 60 centimeters? So again, stop for a second, reread the problem. Every single piece of information is going to be important in some way. So you're going to want to make sure that you circle, highlight, and make sure that you're putting stuff exactly where it belongs. So first of all, this is talking about the volume of a sphere. So we're going to need the volume of a sphere formula, which is 4/3 pi r cubed. So then how fast is the radius increasing? That means that I'm looking for dr dt. Then in terms of things that I know, the volume is increasing 80 cubic centimeters per second. So that means that I know dv dt. So that's 80 cubic centimeters per second. How fast is the radius increasing when the diameter is 60 centimeters? So a diameter is a nice thing to know, and that's going to become important soon. But for now, we only have a problem in terms of a radius. So if I know that the diameter is equal to 60 centimeters, you could, of course, find the radius by taking exactly half that, which means that at this particular moment, the radius is exactly 30 centimeters. If you go back and read carefully, it appears as though that I've assigned all the information. So once you've assigned all the information, you're hoping that once you take the derivative, everything you need is there. If for some reason it's not, you'll go back and find what it is you're looking for. So to take the derivative here, the derivative of v is 1 dv dt. The derivative of 4/3 pi r cubed. So 4/3 pi is a constant. Bring down the 3. 3 times 4/3 is 4 pi r to the 1 less power, and then follow it up with a dr dt. So looking at that, I need r and dr dt and dv dt. So it looks like everything I need is listed. So in terms of solving now, so dv dt is equal to 80 cubic centimeters per second. And that's going to be equal to 4 pi times r squared and dr dt. Remember, we're trying to solve for dr dt. So 80 cubic centimeters per second. When you square 90 centimeters, when you square 90 centimeters, when you square 30 centimeters, you get 90 centimeters squared. So 90 times 4 pi is going to give you 3,600. And then the centimeters are now going to be squared because you square those as well. In order to get dr dt, you're going to divide both sides by 3,600. Oh, sorry, I lost my pi. So 3,600 pi centimeters squared. So your dr dt is going to be equal to 80 centimeters cubed per second divided by 3,600 pi centimeters squared. So that's not only going to help you find your answer, but it's also going to help you make sure you know your unit. So your final answer here, dr dt. So 80 over 3,600 pi, you can actually divide both of those by 80. So when you divide 80 by 80, you of course get 1. When you divide 3,600 by 80, you get 45. So you're going to get 1 over 45 pi. And then if you're dividing centimeters cubed per second divided by centimeters squared, that's going to give you your answer in the unit of centimeters per second. So ultimately here, dr dt is 1 over 45 pi centimeters per second. Again, do you have to put the units in every time? You don't, as long as you're able to get the right unit in the end, but you might want to consider doing it at least at first here. I, again, would strongly encourage you to leave your answer as 1 over 45 pi. If you really, really, really insist on making that a decimal, you would have to plug it into your calculator as 1 divided by, and you would, have to use parentheses around that 45 pi in order to get the right answer. And then you would have to give it to me in terms of the nearest hundredth with rounding. So just make everyone's life easier and leave it as 1 over 45 pi. And that is, of course, centimeters per second. And then make sure you have that pi that I forgot there along the way. All right, here in number 3, a spherical snowball melts in such a way that at the instant when the radius is 20 centimeters, its radius is decreasing 3 centimeters per minute. At what rate is the volume of the ball of snow changing at that instant? So again, we have a spherical situation, and we are again talking about its volume. So that's how we know that the relevant formula is, again, volume equals 4/3 pi r cubed. We are trying to find the rate at which the volume of the ball of snow is changing. So we're looking for dv dt. So then let's see what else it is that we know. So we are trying to solve this problem when the radius is exactly 20 centimeters. So I know that the radius is exactly 20 centimeters. The radius is decreasing at 3 centimeters per minute. So this is the first time that something has been decreasing as opposed to increasing. Hopefully, common sense would dictate that that would mean that the quantity would be negative. So we would say that dr dt is equal to -3 centimeters per minute. So something you're going to want to kind of look out for is when something is getting smaller or shrinking or decreasing as opposed to when it's getting larger. Taking a look here, I believe that is all the pertinent information. So again, let's go ahead and take the derivative. The derivative of v is dv dt. Bring down the 3 times 4/3 pi is 4 pi r squared, followed by dr dt. Are you always going to get that same, derivative? Yeah, every time you take the derivative of the volume of a sphere, you're always going to get that same equation. So it almost kind of becomes like a habit, muscle memory. So that's why we do a bunch of these. So we're looking for dv dt. So dv dt would be equal to 4 pi, then 20 centimeters squared times -3 centimeters per minute. When you go ahead and square 20 centimeters, 20 squared is 400. So 400 times 4 would be 1600 times -3 would be -4800 pi. And then you would square the centimeters to get centimeters squared times centimeters per minute is how you would get centimeters cubed per minute. So that's your dVdt. And again, every time you're doing something in terms of volume, you're going to have cubic centimeters or cubic feet or inches. Anytime you're doing something in terms of area, you're going to have square units. Every time you're just simply talking about a dr or a dd, you're always going to have just in terms of the regular unit. So the more you do of these, the better you'll get at that. And then we've got just one more here to kind of spice things up a little bit. So again, you have a snowball that is melting. This time we're talking about its surface area that is decreasing at a rate of 1 square centimeters per second. Find the rate at which the diameter decreases when the diameter is exactly 12 centimeters. So we're kind of introducing a little bit of a twist here, the fact that we're talking about a diameter. If you're eventually trying to find a variable that is not in your equation, you have to somehow get it into your equation. So if we're trying to find the rate at which the diameter decreases, we're actually trying to find dt. Kind of fun to say. Something else, we haven't thrown any curveballs at you yet in terms of right now, everything has been in centimeters. Everything has either all been in minutes or all been in seconds. There will come a time where those units will not agree, and then you'll have to kind of do some additional work. But again, this is only day one, so we're going to kind of keep it simple. Because we're talking about the surface area of a sphere, we have to use the appropriate formula, which is 4 pi r squared. We're looking for ddt, but let's go ahead and talk about the things that we know so far. So we know that dA dt, the rate at which the area is changing, because it is decreasing, we know that that would be -1 square centimeters per second. Then we know that the diameter is 12 centimeters at the time in question. But unfortunately, our equation only has a radius. So we have to go ahead and in our original equation, we're going to go ahead and change that r into a d. So how do we do that? Well, we're going to remind ourselves the relationship between a radius and a diameter. And of course, the radius is equal to 1/2 the diameter. So that means that in my equation, I am going to replace the r with a 1/2 d. You can kind of write this wherever there's room. I'm going to kind of steal half of this differentiate box and do my work there. So again, I haven't taken the derivative yet. All I'm doing is I'm doing a substitution. So area equals 4 pi. I'm going to replace the r with 1/2 d. Don't forget to square it. So area is equal to 4 pi times, if you square a half, you get a fourth. If you square a d, you get a d squared, which means if I clean that up, I'm going to get that the surface area in terms of the diameter is equal to pi d squared. So that is now the area function that I want to use. And again, that is because of the fact that we are trying to solve for this problem in terms of diameter, in terms of the radius. So we're going to go ahead and get rid of the radius and replace it with the diameter. Now that we've done that, we can go ahead and take the derivative. So the derivative of a is dA dt. Pi is a constant, so bring down the 2 times pi, d to the 1 less power. followed by d dt. So now we're going to substitute and solve. So negative 1 centimeter squared per second is equal to 2 pi times the diameter at exactly 12 centimeters, d dt. So negative 1 centimeter squared per second would be equal to 24 pi centimeters times d dt, which means ultimately that d dt, just trying to find the best place to put that. So d dt would be equal to negative 1 over 24 pi. And then again, if you divide centimeters squared by second by centimeters, you're going to get your unit, which would just be centimeters per second. So d dt is equal to negative 1 over 24 pi centimeters per second. Again, I would implore you to just leave it in terms of pi. If you insist on turning it into a decimal, you have to make sure you put parentheses around the denominator, and then you have to make sure that you round to the nearest hundredth. So that's kind of the end of the lesson for today. Again, focusing just on circles and spheres. I feel like there was something else I was going to mention here. So just make sure, I guess just the negatives, make sure that you're using the negatives appropriately for when things are getting smaller, shrinking, or decreasing, as opposed to when they're not. So you're going to go ahead and try homework number 23. This is the first assignment in your big homework packet for related rates. There are exactly 6 problems. There's kind of the most on the first day to get you started, and then the number will decrease per day. To kind of spice it up, in addition to just focusing on circles and spheres, you also have a cylinder problem, which hopefully makes sense because a cylinder is just a bunch of circles stacked on top of each other. So based on what you've seen today, hopefully it will be pretty simple for you to go ahead and make that leap. So thanks very much for tuning in, guys, and we will catch you next time.